salt power tower systems in SAM. And this is similar in some ways to previous webinars that we've done, but it's been a little while, so we'll sort of recap some of the interesting features or things that you may not be aware of in SAM, which I've called model updates and improvements. And then without too much of that, we'll just jump into a few demonstrations. So we've gotten a few questions about choosing the design point DNI, and then I wanted to tie that in with optimizing solar field geometry and optimizing dispatch, and really get a clear picture of how you go from kind of the initial setup of the case through to an optimized solution. So that will take up the bulk of the time. And then at the end, we'd like to save about 20 minutes for Q&A. Maybe we'll go a little bit over or under, but that's kind of the target. So we'll start here with model updates and improvements. Before we get to that specifically, I did want to just quickly highlight what actually we're modeling here. So I'm assuming that most of you listening are familiar with molten salt power towers, and furthermore that you're familiar with SAM and basically how it works. So I'm not going to spend any time talking about that. If you are not at all familiar with how SAM works, how you actually go about modeling these systems in a very general sense, I would recommend that go ahead and listen along, but you might want to go back and review some of the introductory material in the help menu and other material online after the fact. So, but just to give a quick outline of what SAM models in this particular technology, it's kind of shown here. So we've got a molten salt power tower system, or MSPT, as I'll abbreviate it later, which consists of a heliostat field, which is a bunch of mirrors that track a reflecting vector between the sun and the tower. They reflect the sunlight up onto a receiver on top of the tower, which is cooled by a molten salt that operates between 290 and about 565 or 575 degrees Celsius. That fluid goes into storage tanks and is drawn to generate steam on demand. So that will run with a typical steam turbine, although if you're following CSP, you know that a lot of effort's going into looking at other cycles, such as the CO2 cycle. And so you might see in the future that the steam cycle could be swapped out for something else. One important thing to note about this technology, and what makes it a little bit different from trough systems, if you're more familiar with those, is that the fluid that's used in the receiver is the same fluid that's in the storage tanks, and so you don't have heat exchangers in between the receiver and the storage. And so that enables really more or less a complete decoupling of the solar field operation from the power cycle operation. And that's a key advantage of the power tower system. Okay, so there's really 3 steps to understanding how SAM models molten salt power tower systems in terms of the process involved. The first 2 steps are things that really the user needs to manage. So that is first the design stage. That's choosing the parameters that describe your system, whether it's heliostat size or thermal rating or whatever, and then based on that design, generating a layout or undergoing optimization to generate that layout, and we'll talk more about that in detail. The second stage is an extension of the first, but is managed by SAM, and that is to take the field that you've generated and optically characterize it. So you don't necessarily want to run a detailed analysis of the optical performance of a heliostat field for each hour of the year, because it's it duplicates itself and it's time consuming. So what happens is you generate the field, and then then SAM will go in and select a set of sun positions to generate optical efficiency, create a table, and then when you run the performance simulation, Sam is looking at that, essentially a lookup table to determine the optical efficiency. So we have lookup tables for both total optical efficiency and for the flux distribution on the receiver. Then the third step, which is kind of tied with the second step, then is the performance simulation, and this is really the heat transfer and thermodynamic evaluation of the system over time. One thing that we'll talk a little bit more about at the end here is the operation schemes that are involved. So typically if you're running SAM, you're using what we've started to call the heuristic dispatch. So this is a set of rules that determine when and to what extent power is being generated in the cycle. As opposed to heuristic, you have optimized dispatch, which is considering that operation in a much more robust and sort of planned ahead manner. So we'll talk more about that as we get in here. Okay, so now to the updates and improvements, and I just highlighted a few. There are obviously more that could be included here, but these are some of the bigger ones that aren't often noticed right away, so I just wanted to mention. First, we've added a user-defined power cycle option, so instead of just modeling with the default power cycle performance curves, you can now go in and model your own cycle. And I should mention, I've got a slide for each of these, so we'll talk a little bit more about each of them. The second is dispatch optimization. The third is hourly time of dispatch factors. This allows you to go in and specify for each hour of the year in a table the price that you might get for selling electricity, as opposed to having to do this in the SAM widgets where you select sort of block months and hours of the day and assign values that way. Fourth is improved solar field performance availability specification. So that's a bit of a mouthful, but what that's saying is that you can now go in and manually tweak the performance of the solar field by hour of the year, rather than doing it in big blocks in the same way as the dispatch factors. And lastly, there's user specification of attenuation loss coefficients. These weren't previously exposed, but now you can go in and change how the system evaluates the loss due to atmospheric scattering. So let me just quickly go over each of these. So the user-defined power cycle, this option is available on the power cycle page. If you go to that page, you'll see that there's a drop-down menu below your inputs, and if you select user-defined power cycle, you'll see that there's a whole different set of inputs that become available. And what you can do with this is go through and specify how your power cycle that you want to model depends on the HTF mass flow rate, the HTF temperature, and the ambient temperature. You can also specify interactions between those. So let's say your cycle performance can't be totally predicted by just giving a curve for mass flow and for ambient temperature separately. You could go in and add a second sort of correction curve that deals with how both of those deviating from their design point together might affect performance. There's quite a bit of documentation available on this, and it's not something I'm going to talk about in detail, but just wanted to point out that that's available. The second thing, and again, we'll have a whole section on this later, but we've added this dispatch optimization option, and as I said, by default, SAM generates power whenever energy is available in the storage system. So if your solar field is running and it's accumulating heat transfer fluid in the hot tank, at some point you're going to have enough where you can run the turbine, because the turbine's restricted in terms of being able to run above a certain, say, thermal rating or turn down fraction. So once you reach that threshold, previously, SAM would just turn on the cycle and say, okay, go ahead and run. That may not represent well the times where prices are highest, where you want to be generating electricity. So this dispatch optimization will calculate the best time to generate and determines an optimal operating profile. And you can enable that on the system control page. with the checkbox, and then these inputs become available, and it uses that option. The hourly time of dispatch factors. If you go to the time of delivery factors page, and maybe it would actually help if I showed this. So if we go to this page, you're familiar with this view, which shows different library options for how you specify the price at each hour of the year. Typically, you'd set it up this way, where there'd be a multiplier for each month and hour of the day. But what you can do instead is go up here to the drop-down menu and select the time step option, edit the data, and then input your values for each hour of the year. Or if you're modeling a sub-hourly system, it would be a multiple of 8760. So this allows the dispatch algorithm to more accurately represent sort of current systems that might be interacting in a market where the day-ahead markets are, the price might vary, instead of having these block values. We'll just go back to that. Next, we have the improved solar field performance availability specification. So this shows up on the heliostat field page. And if you scroll down to the bottom, you can see that there's this heliostat field availability dialog, and so we'll do that here. Heliostat field page, and scroll down to the bottom. And this replaces or augments what was available previously, which was to say, I've got this base soiling rate of 90%, I've got a heliostat availability of 99%, but what if you have a system where availability is seasonal, or the soiling rate changes from hour to hour or day to day? Well, you can do that, manage that now by going in here and working within this availability scheduler. So if you wanted to do hourly losses, you could do the same thing, go in and specify a % loss that's incurred for each hour. You can also use the custom periods and say between a certain time window that the loss is a %. And these can all be cumulative, I believe. So all of this is on top of your base rate. So if you just wanted to go in and specify an availability schedule, you might come here and say, well, this should be 1, and then all my availability is handled in this dialog. And I think lastly here, we've got user specification of attenuation loss coefficients. So attenuation has come up as more of an issue recently, because I think people are looking at building plants in areas where the atmosphere is not quite as clear as the U.S. Southwest, where we're accustomed to modeling systems, at least here in the U.S. So if you're talking about building a plant in Spain or in the Middle East, North Africa region, the aerosol content in those locations is significantly different, and in some cases more intense than what we are typically seeing here. So you want to be able to accurately model those conditions and design your system appropriately, and really understand whether that's a serious issue in terms of your design and performance. So normally you would see that aerosol optical depth would be the main driver, and this can vary, as I said, by location and by time of the year. So at the moment we've just got a static D rate, so you'd have to take some average if you wanted to understand what the impact is. We, by default, assume a 25-kilometer visibility, and then for that visibility, there are certain coefficients that go along with it. These come from a study that was done in the 1980s, and we don't really have a lot of good data on this. So if you're looking for, answers on which coefficients to put in here, unfortunately, there's not a lot of publicly available data, and it's definitely an area that needs more attention in terms of research. But I do want to note that the polynomial that you put in here is evaluated for each heliostat position to determine the overall performance of the system. So for example, if we took this default polynomial with our 25-kilometer visibility, and by the way, I'll take an aside and say I don't actually know what this corresponds to in terms of aerosol optical depth, but the relationship here would be that the AOD would increase substantially between 25 and 5, just as a note. So if we replace that clear sky model or that clear visibility model with the hazy visibility model, and this is also from that same study, you can see that there's really a tremendous difference in the optical loss between these two systems. And if you were to do a layout assuming clear visibility, you would get this particular layout over here on the left. If you assume hazy visibility, you get this on the right. You need, first of all, more heliostats on the right, and you tend to get more of a circular layout because heliostats that are further away have a much stronger penalty. So the other thing to note here is that well, I apologize. What I meant to show here was, in both cases, the atmospheric attenuation loss only, and so this should be 91 here. That's correct, but this is showing the total optical efficiency. So I apologize. Don't read into that too much. But the average here would be about 74%. Okay, so that's it for the improvements that I wanted to highlight. So let's move on to the case study and go through how you might choose design point DNI, then optimize the field, then optimize the dispatch. So I think for the sake of time, what I will do here is just march through the slides rather than go back and forth between slides and Sam. But during the Q&A, if you want to go back, if people specifically have questions that aren't in the slides, we can certainly go back and look at the cases that are involved here. All right, so design point DNI, the selection of that is important because with this value, you tell SAM what the DNI is at the design point. If you increase this value, you're indicating to SAM that fewer heliostats are needed to achieve the reference condition power, and vice versa. So if you have a lower DNI, then you're going to need more heliostats to achieve your power. So this goes hand in hand with the thermal rating of the solar field. And you might say, okay, if I've got a solar field that's rated for 700 megawatt thermal, I want to be confident that I'm going to hit that 700 most of the time. And so you'd have to pick a DNI value that you expect to get to most of the time. But you don't want to, go too far either way. And so we'll talk a little bit more about that. SAM uses, for this DNI, SAM uses the sun position at noon on the summer solstice, which is June 21st, or December 21st if you're in the southern hemisphere. So it uses that particular sun condition to evaluate the thermal performance of the system. Okay, so how do you actually select this? Well, if you open SAM and go to the location and resource page and choose a location, you can view the data for that particular location with this button here, the View Data. When you do that, you can then look at that data on an hourly, daily, monthly, however you want to look at it. But in order to choose the best DNI value, I recommend this procedure as follows. So you navigate to the PDF CDF, which is probability density or cumulative density function tab, and this plots out what amounts to these density functions or probability functions that describe how often a particular DNI is observed, or the fraction of DNI that falls below a particular selection. So to say that another way, if you come in here and exclude your 0 values because you don't care about DNI at night, and plot PDF and CDF for beam irradiance or DNI, you can see that for the PDF, there are a substantial number of hours where the DNI is low, say between 0 and 200, but there's a substantial number of hours where the DNI is is high. So it's very likely that if you've got DNI, that it's going to be in this range between, say, 800 and 1,000 watts per meter squared, and that shows up in this PDF. Now, the cumulative density function is showing if I were to choose a particular value, a threshold. Let's say I chose 1,000 watts per meter squared as my threshold. What this CDF is saying is that 99% of the time, the DNI is going to be below that value. So this helps us understand a little bit about how to select the value if we know how often it exceeds a particular threshold. So here, let's choose 95% as our cutoff. Let's say we want a system that achieves its, or that won't exceed its thermal rating more than 5% of sunlight hours. So we look for the 95% value, draw a line over, and then drop down to see where we fall on this CDF plot. So it turns out somewhere around 960, 970, 980, something like that is a good cutoff for this particular location. And this is Daggett. Now, if we look at a different location, say we chose Sevilla, Spain, and looked at our 95% cutoff, now the distribution looks quite a bit different. You don't have such intense DNI there, and so you might choose a value that's closer to 840 at that 95% cutoff. Now, the 95% is pretty arbitrary. It's something that when you're looking through your case, you're going to want to optimize that value. It may be that you go and buy an HTF pump that is rated to just the design power of the system. And so anytime you go above your design point DNI, you're going to have to start dumping energy from the system. So in that case, maybe you'd want to be closer to 100%. Or maybe you have a backup pump on hand and you want to be at your nominal operating condition almost all the time, and so you might drop it down to 700 or something. There's a lot of different options, and it's something that each person who's setting up a case should understand. Okay, so if we look at what the implications are for layout, heliostat field layout at these different design points, I've plotted out 3 different cases, and you kind of have to squint to see the differences, but they're there. So in the 980 watts per meter squared case, if you run an optimization, you get something like 8,324 heliostats, and they're distributed in this way. If you choose 950, now you have 8,660. If you choose 840, now you have 10,100. So there's an obvious relationship between the selection of DNI and the number of heliostats that are required to meet your thermal rating. But a couple things to notice is, first of all, it changes the distribution a little bit. So this distribution is not quite the same flavor as these others. And the other thing to note is that the heliostat count does not scale linearly. So if you just multiply, 900 or 8,661 heliostats by 950 over 840, you don't get 10,163. You get some different number, and that's because as you add more and more heliostats for a given geometry, the ones that you add are the least efficient ones in the system. So you have to add more and more of them to get to your thermal rating. So those are just some interesting observations about choosing design point DNI, and hopefully that gives folks a clearer picture of how to go about doing that. So a couple of caveats, I guess, or pitfalls, things that you want to look out for, are that the DNI design point and the solar multiple are similar, but they control separate aspects of the design. So the solar multiple describes the relative thermal size of the receiver and the power cycle. So the solar multiple of, say, 2 would, for a 200 megawatt thermal cycle, and by thermal I mean that's the thermal input to the cycle, not the gross electric output. would correspond to a receiver of 400 megawatt thermal rated value. That doesn't say anything about how many heliostats you're going to need to get to that 400, but the design point DNI does say something about how many heliostats you need to get to that 400. So these different values are controlling different aspects of the design, and it's important to really draw the distinction because you shouldn't necessarily optimize one without optimizing the other. All right, so I think that's enough on that topic. Okay, so let's move on to optimizing the solar field geometry. So let's say we've now gone and chosen a design point DNI, and we'll, for the sake of simplicity, leave it at 950 because we're close enough for Daggett. How do you go about optimizing the solar field geometry? Well, if we look back and try to think about why are we doing this? What's actually the overarching goals here? The molten salt power tower design process is not as straightforward as other technologies. If you're looking at a trough system from the perspective of just performance modeling, it's fairly straightforward. If you want to add the thermal capacity to a trough plant, you add loops, and it doesn't really require difficult computations. The power towers, on the other hand, require that you generate a heliostat field layout, and that layout corresponds with a receiver dimension. And all of that depends on location and all the different design parameters that go into the system. So if you change the size, the site, the components, you need a new design. Obviously, many variables could be optimized, and there's a fair bit of research going into techniques that deal with overall system optimization. But to keep things simple, SAM optimizes tower height, and receiver diameter. And it also calculates the optimal layout of heliostat positions. SAM's tool to automate this process has kind of two procedures associated with it. The first is just generating a layout given a receiver and tower geometry. And the second is actually optimizing that geometry along with the layout. Okay, so let's look at a case study. And this case study will carry all the way through for the rest of the slides. So we start with the default SAM case and change or ensure that the following values are set correctly. So first, the design turbine gross output. This one should be okay. We're looking at 115 megawatt electric cycle. Now, with the peaking system, put that in quotes because it needs some explanation. What we're considering is a system that, instead of trying to operate as a base load or operate as close to 24/7 as possible, we are designing a plant that maximizes energy production during a small set of relatively high value hours. So you might imagine a market where people turn on the lights in the morning to get ready for work, and that goes from 7 to 9 a.m. And there's a lot of electricity demand. And then during the workday, there's not so much, and then people come home at night and turn on their ovens and everything. And you see this in California, the way the market appears. And there's a demand at night, so you don't necessarily want to be generating right in the middle of the day when PV is generating, when the electricity prices are low. You want to target those high value periods. So that's what we're trying to consider here. So we drop the solar multiple down to something closer to 1 because the number of hours that we're going to be running is not as high as if you were targeting a baseload plant. We specify that the peak hours are as follows: 7 to 9 and 5 to 9 in the evening. And then the multiplier, or the revenue that you get during those time periods, is 3 times the revenue you'd get otherwise. So this is not totally unrealistic, somewhat representative of markets as we understand them today. But obviously, if you are looking at your own market, you'd want to make sure that these are representative. I picked a somewhat arbitrary number of hours of thermal storage, but it's sort of tied with the number of hours that we want to target peak generation. So I didn't optimize this value, but if you add up the hours in the peak hours windows, it's about 8. Okay, so we go into SAM and we specify these values first on the system design page, our solar multiple, our design gross turbine output, our thermal storage. And then we go to the time of delivery factors page and specify our own. And so it might be worth just showing how this goes, because I know people tend to just leave these at the default. So you would go to this page. You would, just to get a clean slate, let's go to uniform dispatch. And then we don't want to use the library values, so we uncheck that. Now we said that there's a second period with 3 times the multiplier, and that was 7 to 9. So we come in here, highlight the ones we want, and then on the keyboard I'm pressing the number 2, and that changes the value to 2. Likewise here, I think we said 5 to 9, 2. And then you do the same thing for the weekend schedule. And now we're set up so that every time the time of day is in this window, you have a multiplier of 3. Just as a side note, you could have gone in here to the time step option and entered a table 8760 that did the same thing. Or if you have a more sophisticated market that you're trying to dispatch in, then you would put in those values there. Okay, now we're talking about field optimization, so we need to take a look at how we've set up the solar field optimization settings. So there's a few things to note here. The first and the most important thing are the initial values that you use. So the initial values are drawn from the inputs in SAM. So if you've got a tower height receiver geometry specified, it's going to start looking for optimal solutions around the point that you've specified already in the SAM inputs. So if you know that you're going to be optimizing towards a smaller system, then you're going to want to update your inputs for your best guess of what you think, where you think it should be looking. You should choose values that are initially feasible. So there is a requirement for the flux limit, and if you specify a system that exceeds the flux limit, the algorithm has a bit of a hard time figuring out where to go, because it's saying, well, I can't work with this. I need to just get to a feasible solution first, and you might end up going into a solution space that you didn't anticipate. The other thing that I would note about the initial settings is that when you do this optimization, you are going to want to run with different initial values. So you might start at a tower height of 200. You might then run another optimization starting at a tower height of 220 or 150 or something, and see whether or not you come to the same answer each time. The optimizer is a tool that helps you improve your design. It is not the right answer all the time. So just keep that in mind. All right, so specific settings, these are available on the heliostat field page. So if we look there, these are available here below the layout diagram. And I won't spend too much time talking about these, but it's just a way of specifying how far you want to jump on your first evaluation. And these are relative, so you'd say, if I start with a tower height of 200 meters and I make my subsequent evaluation, it's going to be plus or minus 6% of that 200. So you'd see plus or minus 12 meters at the next evaluation. And likewise on the other geometry. The number of iterations, this will limit, you'll cut off the algorithm after 200, and it'll just use whatever the best evaluation was at that point. Or if it converges, it'll converge within a objective function tolerance of 0.001. So you can play with that if you want. To run more evaluations, you would make that number smaller. Okay, so if you come in here and actually do the optimization. It can take a little bit of time. It might take a minute or 2 minutes, or it depends on how many heliostats you have in your system. But you'll see this dialog pop up, and this is a iteration by iteration. It specifies the values that it's trying. So with the system that we started with, we were using the default SAM values. It started at a tower height of 193, a receiver height of 21.6, and a diameter of 17.7. And that corresponded to this objective function value here, 1126, flux here, and plant cost here. Now you can see as it starts marching through each iteration, it's saying, well, this is a much smaller system. We're going for something like 360 megawatt thermal on the receiver instead of 7 or 670, I believe, is the default. So it says, yeah, I don't need quite as high a tower. It just starts marching down. Don't need quite a big of a receiver, and it starts marching down. And then the objective function will hopefully improve while making sure that your flux constraint is satisfied. Now, a few things to note. First, the objective function is, in terms of units, meaningless. What it is describing is the total plant cost divided by the expected performance or the expected production of the system over what amounts to about 4 days that it's sampling from. So really what you're looking for here is relative improvement, and don't try to interpret what this is saying as having any sort of units or meaning. The other thing to note is on the flux constraint. This is an approximate constraint, so you might see an optimal solution that's 6 watts per meter above your 1,000 limit. If that's a problem, you can go back and push that limit downwards in your inputs. So you might say, well, optimize for 975 instead of 1,000, and typically what you see is it pushes up against this limit and goes a little bit over. So if it's really important that you don't exceed that limit, go back and be a little more conservative in your maximum flux. So after you run this, you'll get your optimal result here, and that corresponded to in this case, the last one that was evaluated. Okay, after you have a successful run, SAM will notify you that you can update to the optimized values if you would like to. It won't automatically do this, but it shows you a summary of the changes. So as we started out, there were this many heliostats. These were the dimensions, and the optimal solution was this. So it's a little bit more in terms of heliostats, but you're saving costs in the tower and the receiver. So we would click yes and accept that, and it would automatically update the case. One thing to point out, and something to be careful of, is that if you're running with, if you just say, okay, give me a new field layout, but you don't update the other geometry in the field, you can get very weird and not suboptimal results. So this would have been the layout that we started with, and this is the layout after optimizing. You can see just qualitatively that one is better. All right, so after optimizing, you will check different initial values of the variables. You will see that the flux limit is being satisfied, and you might, in terms of addressing the flux limit, you might see that at certain points the flux limit is being violated and the algorithm can't improve any further, but it might have improved if, say, you started with a shorter tower height and a larger receiver to begin with. So you can go back and try those different guess values and see if you come to the same result. Okay, so that is an overview of optimizing the geometry, and I think for the sake of time, I'm just going to keep going here. So now let's say in our SAM case, we've got an optimal solar field geometry, and I think in this case I better put quotes around optimal because it's just an improved geometry. We can't prove that it's truly the single optimal solution, but it's an improved solution. And then based on that, we want to dispatch against our peaking profile. So I've touched a little bit on this, but the motivation is that stored energy can be used over a range of possible times, and determining when and to what extent the energy should be used is not straightforward. So consider that you might, given a particular day of the year when you're trying to operate or simulate, you might have a production forecast, you might have a pricing forecast, you might have known component performance and startup behavior that would depend on weather conditions or operating load or whatever. And you have day-to-day operations that you need to consider. Maybe I want to hold over some energy to start up in the morning or something. So all of those complicate the rule set that you would have to devise to really get the most out of the system. The heuristic approach uses a simple rules to decide when to run the cycle, and it's really just trying to maximize annual energy production. Operates when there's energy available, but it doesn't anticipate future use or needs that are coming later. But on the other hand, the optimized dispatch seeks a revenue maximizing and cost minimizing, so that's like startup costs or ramping costs or whatever, operating profile for both the solar field and the power cycle. So this algorithm determines the operating schedule for both the solar field and the power cycle. All right, how does it work? Well, you start with SAM, the input pages. SAM we'll call the simulation core, which has got the molten salt power tower model. And as it runs through the year, so you have this stepping through time, the CSP controller will say, okay, CSP solver, here are your operating targets. Produce this much energy from the cycle, operate or defocus the solar field. And the solver will then execute those or come to some converged state where all the different components agree on what's happening. So if you're doing the heuristic just, you have a set of rules and you march through and just run the simulation. But if you wanted to do dispatch optimization, now you have to stop about every 24 hours and go out to the production forecast model, say what's coming, get an estimate of the performance of the system and the pricing. And then it goes into this this formulation called mixed integer program. So this is a programming technique that allows you to solve in a complete sense, typically, for the optimal dispatch solution. So I won't talk about that, and we've got a couple papers describing this that we can share. But you generate this formulation, you solve that problem for the next 48 hours or whatever it is, and then you come back with a schedule that you need to execute. So the schedule will then be passed to the controller, and then the controller will go ahead and for the next 24 hours try to match the targets that were established by this approximate but sort of robust solver optimization solver technique. So it does that and it marches through the year. So essentially you solve this dispatch problem 365 times, once for each day of the year, and that each solution corresponds to looking ahead a couple days and deciding what to do today. Okay, there's a number of settings. Again, we're running a bit short on time, so I won't say much about it except that you can choose to penalize starts. So if you have some knowledge of the financial cost of starting up the cycle or the receiver, you might put those in, and the objective when it's deciding whether or not to start up, it'll actually account for those monetary penalties. And when it's making a trade-off between, say, do I operate this hour or do I just hold off, lose that energy, but not have to incur this cost penalty. So those are pretty powerful inputs and really can change the way the plant operates. All right, so to get to some of the results, we ran our case with the original method, and we got annual energy of about 300 gigawatt hours with a capacity factor of 33 and a PPA price of 9.6. And the heuristic, I just pulled a few days, this is in May. you can see that the price schedule here on the bottom, we have our morning spike and our evening spike. And the heuristic model is just turning on the cycle, running until it runs out of energy, turning off, on, off, on, off. Sometimes it hits the peak, sometimes it doesn't. More often than not, it's missing evening production because there's just not enough there. Now, if we enable the optimized dispatch, you can see that it's much more flexible. It's anticipating, oh, I need this morning, I need this evening, and it's hitting much more of those high-value time periods than it was before. You'll also notice that at night, the system would just turn off. But here we actually are able to anticipate and say, well, I can run overnight at the minimum turbine output and then not have to incur my startup penalty the next day. So I'm not wasting energy, I'm not wasting that financial penalty. And it's saying in this case, it's actually financially worth it to just operate through the night at low load and then ramp up in the morning when the price spikes. But that's only some days of the year when there's enough energy available. So we look then at the optimized case and find that the annual energy actually decreases a little bit from the heuristic to the optimized. But what we really care, if we're spending $500 million on a plant, we really care about the revenue. We care about the cost. How cost competitive is this technology? Well, it turns out if you were to run the heuristic, you'd get this answer. If you run the optimized, you get a really substantially lower PPA price. So this means you would be, under these conditions, competitive with this technology in a market at 6 cents a kilowatt hour, whereas in other cases you would not even be close. So this is really an important capability, and it's something that people should be aware of. Now, there are drawbacks to this. It takes a lot longer to run. So instead of running the simulation in, say, 30 seconds, it'll take, 5 to 10 minutes to run a case. But if you're really looking for the best answer in terms of the performance of the technology, at some point, this operation should be considered. So just a few more notes on thermal energy storage. I won't talk about that. One last point I wanted to make on this is that SAM reports both the actual simulation outcomes and it reports the outcomes from the dispatch model. So what the actual performance does is it will go through and run those detailed engineering calculations based on the profile that you're trying to hit. And all those have the same accuracy as SAM has always had. But what we're doing with the mixed integer program formulation is providing an approximate model, so you don't have to run the detailed model twice. You're just looking at an approximate model. And so it reports, SAM will report to you the sort of expectation of what's coming out of the dispatch model, and that's an indication of how well did my actual simulation execute the dispatch profile that was intended. So you see those in the hourly outputs. You can see the ones that are prefixed by dispatch expected. Those are not the actual accurate outputs. Those are just the expectation from the hourly performance model. So, or the hourly dispatch model. So here you can see that there's some disagreement, but in general, they're pretty close. So you might notice when you do this that you see more notices and warnings, and some of them might be a little worrying, but don't worry. We set it up so that it reports anytime there's an issue with solving the dispatch. For a particular day, it'll say that the optimization failed, but just note that it's only for the time window that's specified. So in this case, I think there's maybe 10 or 15 days of the year where there was some issue and the dispatch optimizer couldn't come up with a solution that worked. So it's saying it failed, but that means that 350 days of the year, it's just fine. It's only these 15 days or whatever that were a problem. And what happens when optimization fails is it just reverts to the heuristic model. So it'll just run when it has energy available, and it's not like you're losing out on that energy. If you then go to the notices page, you can get a detailed readout of what happened each step of the year, each day of the year. So each time it runs, it'll report whether it found an optimal solution, a suboptimal solution, or whether it failed. We would typically expect to see almost all optimal solution identified. If you see that in a non-trivial number of cases that there's a suboptimal solution identified, you might want to go back and increase the iteration limit or increase the solver time just to give it more of a chance to find the optimal solution. So it's not, the answers that come back here under suboptimal cases are not incorrect. They're still using the same performance models that we've always used, but they are identifying an operation schedule that's a little bit not as good as what could have been identified. So, okay, sorry, I only left a few minutes for questions, but I think that gives you a clear picture of the dispatch optimization. And at this point, I'd be happy to spend the next few minutes talking.
Thanks, Mike. I think there's a couple questions. The first has to do with the PPA price. If you could show the financial parameters input page. So just kind of wanted to clarify how the TOD factors work and the fact that they are multipliers, the PPA price multipliers, and the PPA price might be specified here as an input if you choose the specified PPA price solution mode, or it might be calculated as a result. So we're running the financial model in specify IRR target mode here. So Sam's going to calculate a PPA price to meet this 11% IRR target, given all the other financial parameters on this page. And then the PPA price would be the value that's shown on the results page. And then those factors on the TOD time of delivery factors input page are multipliers that apply to the PPA price. And then I wanted to ask a question about the optimization penalties.
Okay.
So when those are specified in dollars, so there's like a startup penalty, for example. Does that penalty get applied or get accounted in the financial model? Does it get treated as an operating cost, or is that penalty only used for the dispatch optimization?
Yeah, it's a good question. It's only used for the dispatch optimization. So you could change these values to whatever you want, and it's only accounting for that when it's deciding the schedule. So I don't know if, there may be a limitation, it may not be, but if you do have, if you run a case and you have this a particular outcome in terms of number of starts, you might go back and add, just adjust your O&M, your annual O&M numbers to represent more accurately what you put into these inputs.
Okay, thanks. And then there was a general question about the solar multiple and about how to choose a solar multiple or how to optimize the solar multiple.
Right. So this is, this is a kind of a fundamental question for CSP and one that comes up quite a bit. The solar multiple, as I said, determines the thermal rating of the receiver relative to the power cycle input. So in this case, in the default case, we're saying you want your solar field to be generating 2.4 times at its rated condition the input that's needed for operating the cycle. And what that means is that you're anticipating putting about 1.4 times the thermal rating into storage to use that at some other time, assuming that the cycle is operating at full load. So really, if you optimize the solar multiple, you should be choosing that in conjunction with the best thermal energy storage hours. So we typically do that by setting up a parametric and running solar multiple over a range and running thermal storage over a range and seeing which combination of those is the best, gives you the best financial return or whatever, capacity factor, whatever you're looking at.
Okay, great. And then is it possible to connect SAM with other software to identify hybrid operation of CSP plant, for example, to operate a solar tower with a desal system, a desalination system?
So people may or may not be aware of the SDK and some of the tools that go along with that. SAM is able to generate scripts that you can run and manipulate, and those scripts can be called from Python or Java or the LK language, which is part of SAM's SDK tool. So there you have a lot more flexibility over how to use some of the output from SAM. At the moment, we don't have a way of, say, hooking in directly into the simulation a desal module, but what you could do is run SAM maybe with your user-defined power cycle performance curves, and then after the fact go and run your desal model to see what the freshwater production is or the parasitic implications are, whatever the issue is there.
All right. Here's another question about optimization. Do we need to optimize the geometry of the solar field anytime that we change the solar multiple, or can we change it with the parametrics tool using a fixed solar field geometry?
So this is somewhat a matter of opinion, but if you're changing the thermal rating, if you're changing the size at all in any way of the solar field, I think you probably do need to choose a new receiver geometry and a new field layout and tower height. I mean, ultimately, what would happen is, let's say you are running a parametric over solar multiple, and you don't re-optimize the layout, but you do regenerate the heliostat position, so that would correspond to, say, checking this box, but not the always optimize box. In that case, what you're doing is putting your receiver in a position of maybe going over flux or being way under its design point flux and not performing as efficiently as it otherwise could. So I think you can get like ballpark numbers doing things that way, but very ballpark. And if you're at all trying to replicate a system that you would build or do anything like that, like you really do need to update the solar field geometry for each case that you're considering.
Okay. And could you take a moment just to show the parametrics input page so we can see where that is? Yeah, so this is where you set up the parametric analysis, and we won't go into that right now. I will provide a link to videos that demonstrate how to use the parametrics analysis along with the recording of this video of this webinar on the SAM website. But just so you know, this parametrics page is where you set up a parametric analysis. Looks like there's one other question here. If I change the design input to, say, 6 hours of storage, do I need to change the solar multiple, or does the system determine the field size automatically?
You would need to choose the solar multiple that's most appropriate for your thermal storage. The way SAM is set up is kind of that it takes as inputs the design for your system. So it's really never going to go and update the design without you telling it to. So you would either do that by saying, if I run a simulation, check this box, always layout automatically. That means it's going to generate a new layout whenever you click simulate. If you click always optimize, it's going to always optimize the geometry. But these tools that generate layout and optimize geometry are just ways of helping you, the user, to set up an appropriate case that you want to simulate. Ultimately, SAM is still a simulation tool, but these little widgets kind of help you in the process of deciding how to configure your inputs.
All right, thank you, Mike. I think we're just about out of time, and it looks like we have one more question here. So when using the parametrics tool, how do we know if changing a variable would change a linked variable? For example, if I change the use of water in cleaning, would that change the operating expenses automatically?
Yeah, that's a great question. It's somewhat dependent on, the answer depends on which inputs, which I understand is not very helpful. But typically, if you look in the interface and you see that a particular value is a calculated value, so let's say I ran a parametric on heliostat width, SAM, when it's running, would automatically update the width of the heliostats in the field, but it wouldn't automatically update the layout. You'd have to tell it to update the layout every time you're running a parametric. In the case of water usage, I'm not sure that the water usage is actually linked to anything in the performance, other than just reporting it as a calculated total. I don't know, maybe, Paul, you know the answer to that one.
Yeah, I don't think we have a cost associated with the water usage, so it wouldn't, it would only affect that reported water usage output. All right, well, thank you, Mike. That was a great presentation, and I'd like to encourage everyone to stay in touch with us. If you have further questions about anything that Mike talked about today or anything about SAM, you can contact us. You can either post a question on the support forum, which is on the SAM website, or you can use the contact form on the SAM website to email us if you would rather not share your question publicly. And someone on the SAM team will get back to you with an answer. Then a question about downloading the presentation. So in the next couple of days, we'll be posting a recording of this webinar along with a copy of the slides that Mike used on the SAM website. So just go to the SAM website. There's a resources tab there. And under resources is a link to the webinars page. And you'll find a link to this webinar there. So that it's going to take us a couple of days to get that stuff posted, but we'll do that. All right. Okay. Well, thanks again, Mike.
Yep, and thanks to everybody who participated.
And with that, I think we'll sign off. Have a great rest of your day, and goodbye.